Hello, and welcome to our second lecture for CHY 113. Today we're going to talk a lot about the math involved in chemistry and a lot of the types of units and unit conversions and just sort of how we deal with numbers in a course like this. Chemistry is a quantitative science, and so we will be dealing a lot with different measurements and with different calculations. And so we know how, or we need to know how to deal with those in a consistent manner. And so it's important to remember that all of the numbers that we deal with in a class like this are a lot different than how you might deal with numbers in math. Numbers in math are basically just numbers for the most part, and you're going to be manipulating them and working with them. But the numbers in a class like this represent measurements. And so we need to know how to deal with those. And we also need to know how to deal with very, very large and very, very small numbers. And so that's what we're going to be talking about today. There we go. And so we're going to look at things like units of measurement and what units look like. We're going to talk about metric prefixes quite a bit because that will be a big thing that we have to deal with and work with all semester. We'll look at the differences between precision and accuracy, scientific notation, something called significant figures, which might be new for many of you. And then finally, we'll look at a problem-solving technique or problem-solving tool known as dimensional analysis, which is an incredible tool that I highly recommend that you try to master. And so, like I said, everything that we work with in this class, every number that we work with in this class is going to represent a measurement. And so a measurement is always going to be a number and a unit that goes along with it. And numbers are absolutely meaningless without a unit attached. You can't give an answer of 7.2 without telling what that 7.2 represents. Is that 7.2 meters? Is it millimeters? Is it seconds? Is it liters? Whatever it might be, we absolutely need those units attached in order to give an accurate representation of what that number is. And so in here, in the metric system in general, we're going to be working with various base units. So anytime we're working with length, we'll be looking at measuring in meters, mass measured in grams, time measured in seconds. And when we finally get to energy, the base unit is the calorie, although we'll be working with something known as the joule quite a bit as well. But really, and so we'll be looking a lot at, like I said, meters and grams, and then also volume, which is not on this slide. And the base unit for volume is going to be liters that we will work with. And here's a lot of that information that I just talked about. And so, like I said, the meter being the base unit for length. We talked about mass in the last lecture, that it's a measure of the amount of matter in a substance. Volume is how much space that substance will occupy. And then we'll save energy a little, actually, and talk about that a lot more later on in the course. We also have what we call derived units, which are units that are going to be, as the name implies, derived from a couple of other units. Density is a great example of that. When we calculate density, we divide the mass by the volume. And so density is a measure of how much a certain volume of a sample is going to weigh. What is the mass going to be of a certain volume of a sample? And so it's mass divided by volume, which will lead us to units of grams per milliliter. And so as an example, just to throw something out there, if we have a random sample in which our mass equals maybe 0.672 grams, we know our volume of that sample equals 2.2 milliliters, then we would calculate our density. Density equals mass over volume. So we're going to have our 0.672 grams divided by our 2.2 milliliters. And we calculate that out. Pull up my calculator here. And we get 0.672 divided by 2.2 milliliters for an answer rounded off of 0.31 grams per milliliter. Don't worry about how I rounded that. We'll be talking about that quite a bit when we discuss significant figures later on in today's lecture. But so this tells us then that for every 1 milliliter of this substance that we have, the mass of every 1 milliliter is going to be 0.31 grams. And so remember last time when we talked about physical properties, density is an example of an intensive property because it doesn't matter how much of the sample that we have. Every bit of that sample is going to have the same exact density of 0.31 grams per milliliter. And so again, density is, or the units for density are what we call derived units, because they come from 2 separate units. We derive the units of density by dividing our grams by our milliliters. One of the things that we're going to run into in a course like this is that we're going to have some measurements that are much smaller or much larger than our base unit. And so, for example, if we're working with length, which has a base unit of meters, we might be working with units that are, or a measurement that is really small, maybe down in the thousandths of a meter or so. And so it's more convenient for us to express those in terms of millimeters, where there are 1,000 millimeters per 1 meter. Or maybe centimeters. That might be a measurement some of you are a little bit more familiar with. And in a centimeter, we have 100 centimeters per 1 meter, or even decimeters, or we've got 10 decimeters per 1 meter. And so these prefixes, milli, centi, and deci, are going to help us represent these measurements that are either smaller or larger than our base unit. And so that brings us to this metric conversion chart, which is something that you will essentially just have to memorize and know how to use for the course of this semester. Because there will be many times when perhaps a measurement is given to you in, for instance, maybe nanometers, and we'll take a look at how to use this chart in just a second. But maybe a measurement is given to you in terms of nanometers. For instance, when we start talking about light in a few weeks, quite often light and then the wavelengths of light are given to us in terms of nanometers. But equations that we use, and when we plug that into equations and calculations, are going to require us to convert that measurement over to meters. And so we're going to need to know how to use a conversion chart like this. And so really the way that it works, we can see that the metric prefixes, if you're not familiar with them, are all based upon powers of 10. And so you can kind of view the middle right here, not the middle, but this sort of breaking point here between kilo and deci. This is sort of where our base unit resides. And so anything above this line here, these are all going to represent measurements that are larger than our base unit. And so for instance, if we're talking about grams, kilogram or a kilogram is larger than a gram. There are 1,000 grams in 1 kilogram. And we can see that example here. 1 kilogram equals 1 times 10 to the third, or 1,000 grams. Anything below this line, these are all going to represent measurements that are smaller than our base unit. And so a milligram is 1,000th of a gram, or a millimeter is 1,000th of a meter. There are 1,000 millimeters per 1 meter. And so there are many different ways to go about converting and using some of these conversions. One of the simplest ways, let's just shrink this down a little bit so we can bring up our whiteboard at the same time. One of the ways that we can use this conversion is by simply moving our decimal points around. And so let's say we have a measurement of maybe 0.022 meters, and we need to convert that over to millimeters. So we look on our chart, and again, we see that, or we know that our baseline meters is sort of right here in the middle, and we're converting to milli. And so we look at our exponent here for milli. We can kind of ignore the sign for this, and we'll see why in a second. But we see that our exponent there is 3. That tells us that we're going to need to move our decimal point by 3 spaces in order to convert from meters over to millimeters. Now here's where we can just sort of think about things a little bit. We know that we're moving from meters to millimeters, and so we're moving from a larger measurement to a smaller measurement. That means that our number has to get larger. Think of it this way. If you're converting between dollars and cents, if you have $2 and you're trying to convert that over to cents, then you're moving from a larger measurement in dollars to the smaller measurement in cents. So that means the number is going to get bigger. And so we're moving from $2 over to cents. Our conversion there is 100. No coincidence, centi, 100. That's where it comes from. And so to go from $2 over to cents is going to be 200 cents. Our number goes from 2 to 200. The number gets larger. Same idea here. Our number is going to get larger because we're going from a larger measurement of meters to a smaller measurement of millimeters. We look at our metric conversion chart. Our exponent for milli is 3. That tells us that we're going to move our decimal point by 3 places. Here's our decimal point here right now. We're going to move it 1, 2, 3 places. There's our new decimal point for an answer then of 22 millimeters. And we would do the same exact thing if we're going the other way, if we're moving in the opposite direction. Let's say we're working with watts, and we have a measurement that is this many watts, and we want to convert that over to gigawatts. So again, we look at our conversion. We can see that our, sorry, that keeps sort of flipping like that. My mouse is sort of sensitive. But again, here's our baseline. So we're sitting right here in the middle with watts. Our exponent for giga is 9, because there are 10 to the 9th, or 1 billion watts per gigawatt. And so our exponent is 9. Here we're moving from a smaller measurement up to a larger measurement. And so our number's going to get smaller. Again, think of our dollars and cents example. If we have 150 cents and we want to convert that to dollars, then we're going from a smaller measurement to a larger one. And so our number of dollars is going to be smaller than our number of cents. And so in that case, we would be moving from maybe 150 cents to $1.50. So our number gets smaller because our measurement is going up to a larger measurement. And so same idea here. So we know that we have to move our decimal point 9 spaces. And then our number has to get smaller. So we're going to move our decimal point 9 spaces to the left to make our decimal point smaller. And so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's our new decimal point. And you'll see situations like this sometimes when you're moving your decimal points around. And that's why I specifically leave these little humps in here like this. Because now those humps are just going to represent zeros that we're going to now put into our measurement. And so we're going to put those zeros in front. So there's our new decimal point. Those 2 zeros that are resulting from our little humps right here. And then 1, 2, 1 gigawatts. And so 1,210,000 watts are going to represent 0.00121 gigawatts. And so that's one way to do these conversions, is simply moving your decimal point around. Incidentally, you'll notice here that what I did, so we have a number that's smaller than 1, so we have our decimal point. You'll notice that I put a 0 in front of the decimal point. You want to get in the habit of always doing that. That just, it's much more clear when you do that rather than just writing writing 0.0012. It just removes any ambiguity of somebody might be looking at your paper saying, okay, well, is that really a decimal point, or is that a speck on their paper? Did they accidentally, scribble something out? What is that little symbol there? What is this actually standing for? And sure, I mean, it might be somewhat obvious to you because you know what it is, but it might not be obvious to somebody who's looking at your work. So if you just always get in the habit of putting that 0 in front, that's pretty standard in all of science. You will never find a piece of scientific literature that does not have that 0 in front of a measurement like that. I guarantee it. And so you want to get in the habit of putting that 0 there. That's just sort of an aside. Okay. And so let's say, though, that you're maybe moving from one metric prefix to another, rather than just simply going back and forth between the base units. It's the same exact idea. You're going to just move your decimal point around. And so maybe we're moving, for whatever reason, we are going from maybe 11.2 micrometers, and we need to convert that over to nanometers. Same exact idea. We can see that we're looking at micro here, which is 1/1,000th, has an exponent of 6. We're moving to nano with an exponent of 9, difference of 3 decimal points, 3 powers of 10. And so we need to move our decimal point 3 places. And we can see that we're going from a larger measurement to a smaller measurement. So our number is going to get bigger, which means our decimal point, just rewrite it right here, our decimal point has to move over to the right. And so we're going to move it to the right 3 places, 1, 2, 3. These little humps now, again, remember, are going to represent zeros. Here's our new decimal place. And so our conversion then is going to be we get 11,200 nanometers. So same idea. Only we're just sort of we're just moving through, or we're not going through the base unit necessarily. But it's the same idea. We're just going to be moving our decimal point around. And so that's one way to do these metric conversions. When we talk about dimensional analysis in a few minutes, we'll see another way to do metric conversions, which sometimes is a little bit more convenient because you oftentimes won't be doing metric conversions just sort of on their own like this. You're not necessarily going to be called to just convert 11.2 micrometers to nanometers. Certainly in homework or in the tests, especially the first exam, yes, I'm going to have some questions in there where you're simply doing these conversions. But more often than not, as we start getting into the semester, you're going to have to do these conversions just as part of an overall calculation. And sometimes it's easier to slide it in there as one of your steps in dimensional analysis, which we'll be talking about in a little bit. And so, okay, so let's move on from metric conversions. Although before we move on too much, just to remind you and point out that if you go to the course website, I'm in the homework tab right now, but here's your landing page for the course website. Remember that there are lots of different tools for you under the material. So we're still in Unit 1. Right now we're looking at tools of quantitative chemistry. So this is all the tasks and what you should be doing for today's lecture. And so we've got all these different objectives here. And so for objective 1, we're talking about measurements now. You should be, again, reading these sections in your textbook, but also these various videos. And so we just talked about metric conversions. And so you should watch this course video, metric conversions. It's supplement. These are supplemental videos that go along with everything that we talk about. And another place that you can find these, so you'll find all these videos here under the objectives page, but also if you go to Unit 1 materials, for one, you'll find the lecture slides, so all the slides that are making up the basis of the lectures. But then here's some videos. So right now we're under objective 1.2, which again is this tools of quantitative chemistry. And here are some various videos that I've made. And so there's the metric conversions. The other thing that you will find are lots of practice. And so metric conversions, click on this, and here's just a whole bunch of practice. And so some of this you'll find helpful, some of it you might not. That's what they're here for, though, is if you do find them helpful, you should do them. And so this one, for instance, just has you really starting to look at, okay, how am I moving my decimal point? How many places do I have to move it? Am I moving it left to right? And it's sort of really just getting you to think about how your measurement's changing and by how much. And then doing a bunch of converting. And then just a whole bunch of different metric conversions there. And all these extra practice problems that you find have the answer keys. And so keep that in mind as you're working and studying, that this unit materials page has a whole wealth of other sources for you or other resources for you to study and to master this material. But then also remember that all of these objectives pages really go through the tasks that you should be completing, again, in order to master this material. So back to our lecture. Another tool that we are going to use in order to work with very large or very small numbers is scientific notation. And scientific notation is probably something that you've been exposed to at some point during your education. But scientific notation is always expressed as a number in the ones spot, followed by whatever we need for numbers past the decimal point. And those numbers will be dictated by significant figures, which we talk about later on. And then times 10 to the whatever power. And so, for instance, let's see how we convert that distance to the sun, 93 million miles. Let's see how we convert that to scientific notation. And so we have 93 million, and our decimal point is now right here. What we need to do is to get our decimal point to here. So scientific notation, we need a number in the ones spot followed by our decimals. And so we need 9.3. And so what we need to look at is how many spaces we have to move our decimal point in order to get there. So we're going to have to go 1, 2, 3, 4, 5, 6, 7 spaces in order to get to 9.3. And so we're going to have 9.3 times 10. Now we moved our decimal point over to the left, which means that we're going to have a positive number here. We need our units because numbers are meaningless without them. Hopefully some of you noticed that up here, that I left those off. We should always have our units. But again, so let's just think about the positive versus negative number here. When we have this positive number, that means that our number is going to get larger. So times 10 to the 7th. And so again, think of that maybe in terms that you're a little more familiar with. 10 to the 2nd is going to be 100, right? 10 times 10. And so that would be, in this case, if this were the second, then it would be 9.3 times 10 to the 2nd. So 9.3 times 100, which means that our number would get bigger. And so if we're going in the opposite direction, we're just going to sort of confirm that this works. So 9.3 times 10 to the 7th, we're going to go 1, 2, 3, 4, 5, 6, 7. There's our new decimal point. And any of these little humps become our zeros. So that's the same thing that we have written up here. Let's look at this other example. The radius of a carbon atom. Carbon atoms are very, very, very tiny. That probably doesn't come as any surprise to anyone. So carbon atoms are very, very, very small. And so the radius of a carbon atom, I've got to stop here and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros there. So the radius of a carbon atom is 0.00000000070 meters. Not real convenient for us to think of it in those terms, or even to write that out and to work with that sort of number. Now, yes, we could convert over to a metric prefix, and we could work with things that way. Like I said, there will be quite often when we have to use certain units because that's the form that we need for a certain calculation. So we need to keep this in meters. Maybe we're using our light equations that we'll be talking about in a few weeks. And so we need meters for this particular calculation. And so, again, we want to convert this over then to scientific notation. And so our decimal point is here right now. Decimal point's here. We need to get our decimal point here after the 7. And so we are going to have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spaces. And so we get 7.0 times 10 to the negative 11th meters, because we moved our decimal point over to the right. And so it's going to be negative 11. And so 7.0 times 10 to the negative 11th. And so that's scientific notation. When you're working with scientific notation in your calculators, and this, by the way, is the reason why you need a scientific calculator for this course, because a sort of a regular, so your basic calculator without scientific notation, or your non-scientific calculators can't handle numbers like this. And we're going to be dealing with numbers that are even larger and smaller than these. When we deal later on with Avogadro's number is 6.02 times 10 to the 23rd. And so that ends up being, when we convert that out, 602 with 21 zeros after it. An incredibly large number. Regular calculators that are not scientific cannot handle numbers like that. And so we need scientific calculators that are able to deal with scientific notation. And so the way that you use scientific notation with your calculators, and some of this will depend on the type of calculator that you have, but what you want to look for is a button that looks like this. It'll be either EE, sometimes I've seen some of them with lowercase, some of them with uppercase. Sometimes you see EXP, sometimes you see times 10 to the N. Any of those, when input into the calculator, take the place of the multiplication symbol, 10, and then your little caret for the exponent and whatever your number is after that. And so if I have, in this example, scientific notation of 5.65 times 10 to the 4th, I'm going to put that into a calculator as 5.65 EE4. So let's look at an example here. Where's my calculator? There it is. And so the way I would put that into this calculator, we can see here that it's EE. Note that it is not the same as this 1E. This 1E is a number that's used in natural log calculations, which is not something we'll be dealing with in this course. But anytime that an E is used for scientific notation, you'll see it like this. It'll be the EE. And so here we've got 5.65 EE. And I'm a little confusing on this because then it just puts in the 1E there, but 4. And so this now tells the calculator that it's 5.65 times 10 to the 4th. this is very important. If you do not use this EE button, you may run into problems down the line with how your calculator is viewing a number. Because your calculator is always going to follow a very strict order of operations. And so let's look at just a quick example. Let's say we're maybe working with this one here. And so we've got 5.65 times 10 to the fourth. And let's say maybe whatever calculation that we're doing, maybe we're doing a density calculation, and this is our volume. So these are the number of milliliters that we're working with. We have a mass that's maybe equal to, I don't know, 2.23 grams. Just throw an example out there. So we're calculating our density. So we're going to set up our calculation. D equals M over V. 2.23 grams divided by 5.65 times 10 to the fourth. Now, if you just plug that into the calculator as is, if you just go to your calculator and you type in 2.23 divided by 5.65 times 10 caret 4, your calculator is only as smart as what you input into it. And your calculator will always follow the strict order of operations. And so let's see what that looks like here. So we put in clear this out. 2.23 divided by 5.65 times, I'm just looking for my little caret. I'm not used to using this calculator. We'll just go 10 to the fourth. I'm not sure if that actually worked it out right, because again, I'm not used to working with this. Forget that example. Sorry. Let's just come back to here. What this is going to do is it's going to first divide your 2.23 by the 5.65. Your calculator doesn't know, if you've input it like this, your calculator doesn't know that this 5.65 is supposed to go with the 10 to the fourth. And so it's going to do this calculation first. It's going to do your 2.23 divided by 5.65. Then it's just going to go ahead and multiply that answer by 10 to the fourth. Again, it doesn't know that those are supposed to go together. Now, yes, you could be very judicious about using parentheses, and if you put this in parentheses into your calculator, then you would probably be okay. But it's just so much easier to simply use that scientific notation. And so instead, you would put this into your calculator as 2.23 divided by 5.65 EE4. Because that tells your calculator that this stays together. It tells your calculator that this is scientific notation and that this is 5.65 times 10 to the fourth. And that's all supposed to be one number. And so get into the habit of doing that. Get into the habit of using this EE button. It will definitely save you a lot of heartache down the road. If you, depending on what you are using for a calculator, if you're unsure what it is, then go ahead and, we can hop on some Zoom office hours at some point, and you can literally hold up your calculator, show it to me, and we can we'll try to figure it out together. And I'll show you as best I can over a Zoom meeting. I'll try to show you how to actually use it. Or literally, if you want, snap a picture of your calculator and shoot it to me in email, and I can walk you through it. But using this EE button to represent your scientific notation, excuse me, it is going to be very important for you going down the line. Okay. So switching gears a little bit here, again, we have to, remembering that our numbers in chemistry and our numbers that we use in this course are going to represent measurements and are going to represent data. We have to consider how good that data is. And so we have two different terms that we're going to use to try to indicate how good a set of data is. Precision of a data set is going to indicate how close all measurements are to each other. And so usually, and you'll see this when you take lab, when you're in 114, you'll never take just one measurement and say, okay, measurement done, that's it. You're going to take a series of measurements most of the time and then compare them to each other and average them out to get your actual measurement. And so precision is going to indicate how close all of those measurements are to each other. Whereas the accuracy of those measurements, the accuracy of really the average of those measurements, will indicate how close the measurements are to the true value, what they really should be. And so we can see this example here. We have 3 mass readings of a 7.5-pound infant taken on 4 different balances. So we can see balance A, B, C, and D here. And so we look through these different trials, and we can see that on balance A, all the trials really are pretty close to each other. They're all right in that 7.5, 7.4 range. And so they average out to 7.5, so they're really accurate because our average is coming out very close to what the real number actually is. Not only are they accurate, they're also very precise because all the measurements are close to each other. Here we have an example on balance B where we're getting precise measurements. All the measurements are close to each other, but they're not accurate. Our average is coming out to 8.1 compared to the true weight of 7.5. And so the measurement is not close to what it should be, but they're all close to each other. This tells us that probably what's going on here is that there's something that is the same going wrong each time. The same error is being made in this measurement each and every time, throwing it off by just a little bit. Here we have a set of measurements that average out right on. However, they're definitely not precise. The numbers are all over the place. This one would be a little bit tougher to correct for. We don't know what's happening. It's tough to say. And so this would not be a data set that we'd like to see because we don't know how to correct for it. And then finally, this one is just a hot mess. Who knows what's going on? We're definitely not anywhere close to the actual average. Numbers are all over the place. We would just throw this data set out and start over. We have no idea what's happening here. And so we have precision and accuracy to try to let us know how good a data set is and how reliable it is. Can we actually trust this set of data? And so you'll be looking at ways to quantify both the precision and the accuracy when you're looking in lab, when you're doing lab later on, using things like average and mean and standard deviations, percent error, and some other tools like that. We won't be working with those things much in this course, but you'll definitely be looking at that in lab. Which now brings us to something that we call significant figures. And so we have to remember, like I said, that we're working with measurements in a course like this. And so a measurement is only going to be as good as the device that we're using to take that measurement. And so a good example are these types of balances here. We can see this balance here on the left. We're measuring what looks like maybe some copper sulfate, little blue crystals in there. This balance can only measure to the 10th spot. And so we get a mass of 10.4 grams. This balance, however, much more accurate. You can see that now we can actually measure out to the 10,000th of a gram. So we're measuring out to 4 decimal places. Incidentally, there's a huge cost difference between these two types of balances. This balance here, you could probably buy for about $100 somewhere. balances that will accurately and reliably measure out to 4 decimal points like this, to the 10,000th of a gram, now you're up in the thousands of dollars for this balance. Some of these can run upwards of even $10,000 for a balance that goes out that far. So it's just sort of a side note that precise science can be expensive, or accurate science. And so yeah, so again, we're always going to be hampered in a sense by how good our measuring device is. And so with that in mind, we have to remember that a calculator is always going to just spit out an exact calculation and spit out tons of decimal points for us. We can't report all the decimal points that the calculator gives us, because in doing so, we are representing an accuracy of the measurement that isn't really fair for us to represent, because our measuring device to begin with was not that accurate. And so let's take a peek at an example. Yeah, okay. So sorry, I want to leave it right here for a minute. But let's look at an example here. And so let's say we're going to use density again as an example. So we're trying to find the density of an object, and we measure the mass of this object to be 6.72 grams. So we have a measuring device here that is capable of measuring to the hundredths spot. And so we have to remember that this last point here really is sort of an estimate. And what the measuring device has done, what the balance has done, is it's rounded whatever the actual mass was, it is rounded to get to this 2. And so realistically, this 6.72 actually is anywhere between 6.715 to 6.724. The actual mass is anywhere within this range. And we don't know exactly where it is, because the measuring device that we're using, again, can only go to the hundredths spot. And so it's reporting as 6.72. The actual mass could be maybe 6.721465. We don't know that. All we know is that it's about 6.72, because that's what our measuring device is capable of reporting to us. And so we know that the actual measurement is somewhere in this range here. And so then we also measure the volume. So we use a graduated cylinder, and we measure the volume of this sample to be 8.51 milliliters. Now again, this last measurement here is actually estimated. And so if we have a very crude drawing, perhaps, of a graduated cylinder over here, use our graduated cylinder. And let's say it's marked off something like this. There's 8, and again, this is a very crude rendering, but there's 8 milliliters, 9 milliliters. So here's 8.5. And let's say that our actual liquid level in there is sitting like this with our meniscus. And so we can directly measure in this case the 8.5, because we have markings that go to 8.5. But then we estimate ourselves and we say, well, the meniscus, our line here, is slightly above that. And so we estimate that last point to be 8.51. Now again, that last point is estimated. And so realistically, that tells us that our measurement is really anywhere between 8.505 milliliters to 8.514. Any volume measurement within that range is going to give us a volume of 8.51. And so keep that in mind. We're going to return to these numbers here in just a second. But again, let's say we're looking to calculate density. So we're going to use our density formula. D equals M over V. And so we're going to put our numbers in here. We're going to get 6.72 grams divided by 8.51 milliliters. And we plug that into our calculator. And our calculator is going to return to us an answer of 0.789659224. And again, our units are grams per milliliter. All right, I'm just going to go ahead and erase my little, well, maybe. Here's my erase tool. Okay, I'll leave it. There we go. Sorry, I just want to get this out of the way. Okay. And so that's what our calculator is going to return to us for an answer. But again, we know that our measurements are actually in these ranges here. And so hypothetically, the density could be as small as, if we use the smallest of the range for our mass, our 6.715, that's the smallest that our mass could be, and still return 6.724 for our measurement. And then the largest for volume could be 8.514 milliliters. That's going to give us, plug that into our calculator. And so the real density could be as small as 0.788-70096 grams per milliliter. Or our density could be as large as, using our largest number for mass, our largest possible number of 6.724, divided by our smallest possible number for volume, 8.505. Plug that into a calculator and we get 0.7905937 grams per milliliter. And so that's the largest that our density could possibly be. And so based upon our measurements of 6.72 grams and 8.51 milliliters, and knowing that those numbers actually represent a range, but those are the closest that we could get due to the accuracy of the measuring devices that we were working with. That means that the real density of this object is somewhere between 0.788700096 and 0.7905937. So our real density is somewhere in between these two numbers. It's somewhere in this range. And so that means that we can't simply report what our number was. Remember, if we go back, the number that was returned to us in our calculator from our calculation was 0.789659224. We can't report that whole thing, because reporting that whole number out implies an accuracy to that measurement that isn't real based on what our measuring devices were. Based on our measuring devices, we know that the actual density is in between these. And so we use significant figures, and we'll look at the rules for determining numbers of significant figures in just a second. But we round our calculated answer to the correct number of significant figures, which then helps us to represent the accuracy of our measuring devices. And so in this case, we're going to round to 3 significant figures. And so we're going to take our answer here that we got, round it off to 3 figures, which means that we're going to cut our answer off right here. And so we cut our answer off right there, and we're going to round it then to 0.790 grams per milliliter. And this is the answer that we would then report to a correct number of significant figures. And so the whole idea behind significant figures is that we will use them to round answers to an accuracy level that represents our measuring devices. And we always have to round to the number of significant figures that are in our least accurate measuring device. Our answers can only ever be as accurate as the least accurate measuring device that we were working with. And so in this case, and again, we'll look at how to calculate this number in a second, but we had 1, 2, 3 significant figures in our mass measurement. We had 1, 2, 3 significant figures in our volume measurement. And so the least number of significant figures was 3. And so that's going to be the number of significant figures in our answer is 1, 2, 3. Let's say we had a cheaper scale. Let's say that the balance that we were using could only go to the 10th spot. And so instead, erase went a little bit wild there. Let's say instead we could only measure that it was 6.7 grams. And so now we've got 1, 2 significant figures in our mass measurement, 1, 2, 3 in our volume. Our least number of significant figures in our measurements is 2. And so our answer in that case would only be able to be recorded to 2 significant figures. And so we would, instead of 0.790, have to report 0.79. Now, incidentally, and this is going to lead us nicely into talking about our rules for significant figures, there's absolutely a difference between these two numbers. Mathematically, no, there's no difference between them. But as a measurement, this number is much more accurate than this number, and that matters. And so let's take a look now at our rules for determining the number of significant figures, the number of significant digits in something. Anytime you have a non-zero, so this is where you're going to be looking at a measurement and counting how many significant figures are in that measurement. All non-zero digits are what we call significant. And so here we have 3.45, all non-zeros, so there are 3 significant figures there. Zeros that come between non-zeros are also significant, whether or not there's a decimal point there. And so this is 0 here. So really, when we're looking at significant figures, if it's a number, if it's an actual non-zero number, that's significant, just no matter what. And so where we need to really set our rules and talk about our rules come with how we deal with zeros. And so in this case, with a 0 appearing between 2 other non-zeros, that is significant. That is a significant figure, a significant digit. If we have a 0 following a non-zero digit and to the right of the decimal point, that is significant. That's where I was just giving the example of if we have something like the difference between 0.4, maybe 0.4 meters versus 0.40 meters. This is a measuring device that is much more accurate, and we're able to pull that out to the 100th spot, as opposed to this measuring device, which doesn't have that same level of accuracy. And so this 0 is significant. And so there's a couple ways to think of it. One of those ways is just by using the rules that we're looking at here. And so in this case, we have a non-zero digit, or sorry, we have a 0 following a non-zero digit after the decimal point. So that means it's significant. Another way to think of it is just start asking yourself, is this 0 something that represents some inherent accuracy in the measurement, or is it just what we call a placeholder 0? Is it something that just tells us where our measurement begins and gives us maybe some reference to the decimal point. Something like this. This is a placeholder 0. This isn't part of the actual measurement. It's giving us information as to where the measurement starts. And so our next rule, again, starts to deal then with those placeholders. If there's no decimal point, then zeros following a non-zero digit are not significant. They're merely placeholders. And so in this case, we have the 6,000. There's no decimal point here. And so these zeros following the non-zero digit are just placeholders telling us where our measurement actually starts. And so there's only one significant figure in this measurement. However, now we put a decimal point here. This decimal point right here tells us that that's where our measurement actually really starts. That the placement of that decimal point now means that all those zeros are significant. And so this number, the 6,000 point, would have 4 significant figures. Zeros that appear before non-zero digits, whether or not there is a decimal point there, are non-significant. Again, they are just placeholders. And so these 3 zeros here, not significant. They're just telling us that our measurement actually starts in the 10,000th spot. However, this 0, if we apply our second rule, this 0 is a 0 following a non-zero digit and following the decimal point. So it is significant. So we have 2 significant figures there. Scientific notation is another tool or another way to use scientific notation. Another thing it's useful for is it also removes any ambiguity surrounding significant figures. All digits expressed in scientific notation are going to be significant. And so here we have, or in that example below, it was, sorry, 2.30. I think that's what it was, wasn't it? There it was, yeah. Times 10 to the 4th. That 0 is significant. And so that's another way that scientific notation is useful to sort of remove any of that ambiguity. If you see a number express a 0 in scientific notation, it is significant. And so maybe, you know, that number of 6,000 we were looking at before, just written like this, tells us there's only one significant digit there. Maybe the measurement actually was a little bit more accurate than that, though. Maybe this second 0 here really is significant. There's no way to tell that with the number written like this. If we convert this to scientific notation, however, and we include that 0, now that tells us that 0 is significant. And so it's a way to help us help us show us the accuracy of our measuring device using significant digits. And scientific notation can help with that. And so significant figures are another thing that we are going to be using constantly throughout this course, because all of our numbers are going to represent measurements. And so we have to take the accuracy of our measuring devices into account. And so the way, another factor in significant digits is that we've got measured numbers, but we also have exact numbers, and so numbers obtained by counting. There's no uncertainty in those, and they would be considered to have an infinite number of significant figures. And so, for example, maybe you're finding the average of 3 different measurements. When you're finding that average and you divide by 3, you do not take that 3 into account for your significant figures, because that is an exact counted number, and it's considered to actually have an infinite number of significant figures. So keep that in mind, the difference between measured numbers and counted numbers. And so in calculations, if you're multiplying or dividing, the final calculated answer cannot have more significant digits than the measurement with the fewest number of significant figures. And so, in other words, again, if we're looking at density calculations, if we have a density and we're calculating, just throw some numbers out there, maybe 8.542 grams divided by 2.5 milliliters, We plug that into a calculator. Let's just see what we get. We get 8.542 divided by 2.5. And so our calculator is going to spit out to us 3.4168. But we look at our significant digits here and we see that we've got 1, 2, 3, 4 significant figures in our mass measurement and only 1, 2 in our volume measurement. And so our least number of significant figures is 2. That means that our answer needs to be rounded to 2 significant figures. And so our answer would be expressed as 3.4 grams per milliliter. A note on rounding, if I remember right, your book, I think this textbook that we're using, has some different rounding rules when it comes that you might be familiar with when it comes to how to deal with fives. And honestly, I don't remember what those rules are off the top of my head. I'd have to go back and look. As far as I'm concerned, use the standard rounding rules that you've always learned. Round down if the number is below 5, round up for 5 and above. So just sort of keep that in mind when you're looking at rounding. Okay, and so let's just look at another quick example here. So we have 6.50 grams divided by maybe a really precise volume measurement now of 1.2046 milliliters. And so again, we plug that into a calculator. The calculator spits out to us 5.3959820069. But now we have to go back and look at our actual measurements. 1, 2, 3. This 0 is significant here because it's a 0 coming after a non-zero after the decimal point. So we have 1, 2, 3 significant figures. We have 1, 2, 3, 4, 5 significant figures in our volume. And so our lowest number of significant figures is 3. And so our answer has to be rounded to 3 significant figures. And so we're going to get 5.40 grams per milliliter. And so when multiplying or dividing, simply find the least number of significant figures from your measurement and round your answer to that amount. Now the rules are a little bit different when it comes to adding and subtracting. When you're adding and subtracting, what you're actually looking for is the places past the decimal point. And so your final answer should not have more places past the decimal than the measurement with the fewest past the decimal. I know it's kind of wordy, so let's just look at an example. So let's say we've got 3 different numbers that we're adding up, 3 different measurements. Maybe we've got 3 different times and we're adding them all together. So we have 1.1, these are all going to be, so this is just time. In seconds, we have 1.1, 2.26, and maybe 1.178. So we're adding all those up. We get 8, 13, 1, 2, 4, 5. So we get this for our number added up. But now what we have to look for is the fewest number of places past our decimal point. And we can see that we have that here in our first measurement here, only goes to the 10th spot. And so that's our cutoff. And so our answer here is going to be 4.5 seconds. And so we look at just another quick example, maybe 2.6, 3.4524, and 7.163745. Throw an example up. So again, we add those up. 6, 11, 12, 1, 3, 6, and we get 13.216145. So again, though, we need to look for, since we're adding and subtracting, we're going to round this to 13.2. And so adding and subtracting, we look to the least number of places past the decimal point, and that's where our answer is going to go. So again, you can find lots of practice on the website and another instructional video that will help to clarify some significant figures for you. Oops. Okay, finally, dimensional analysis is an incredible tool that will help you with calculations and will help you run conversions. And so the way that it works is it works by looking at what the units are and how to set things up in order to convert from one unit to another. Instead of looking at this example actually with energy here, let's look at an example that we're probably all somewhat familiar with. Let's say that we want to know the number of seconds in 20 years. And so we have 20 years, and we're going to convert that over to seconds. For simplicity, we're going to forget about leap years. We're not going to worry about leap years in this calculation. Now, this is a calculation that I guarantee you would all know how to do. Because what you're going to do is you're going to take your 20 years, and then you're going to multiply that by 365 days in a year. Multiply that by 24 hours in a day, times 60 minutes in an hour, times 60 seconds in a minute, and you're going to come up with an answer of about 63 million, or sorry, yeah, 63 million 70, wow, nice work with my commas there. Let's fix that. That looks better. 630,720,000. And then we'll actually say that these are, or this 20 years is exact. All these conversion factors are exact numbers. So every number we're working with is exact. And so we don't have to do any rounding for significant figures. So we come up with this number here. And so this is dimensional analysis. What you've done in order to do this calculation is you've used a series of what we call conversion factors that allow us to convert back and forth between different units. Let's look at just the units here for a second. Let's take out the numbers completely. If we are looking at just the units, and we're looking at everything up above versus everything sort of down below, then we have years times days times hours times minutes times seconds. And then down below, we have years times days times hours times minutes. And we know that anything divided by itself is 1. And so that means years can cancel out, days can cancel out, hours can cancel out, minutes can cancel out, and we're left with seconds, which are the units that we were looking for. And so dimensional analysis makes use of these conversion factors to convert back and forth between different units. Because let's say we were going the other way. Let's say we knew that we had 630,720,000 seconds, and we wanted to convert that to years. Then we're just going to go in the opposite direction. But what we're going to do is take these conversion factors and just flip them around. right? Because if we're going from seconds over to minutes, then we're going to go, we've got our 630,720,000 seconds, and we're going to go 1 minute for every 60 seconds and divide those to come up with our minutes and then carry the rest of the calculation through. And so that's the key thing to recognize about conversion factors, is that conversion factors can be set up either way depending on what direction you're going with the calculation. So let's look at that even closer. Again, we'll stick with this sort of time example. But we've got a conversion factor. We know there are 24 hours in a day. We also know that one day consists of 24 hours. I can write that conversion factor either way. It doesn't matter. Either way is an identical expression. And so if I'm converting from days over to hours, let's say I have 3 days, and I want to know how many hours that is, then I'm going to use this form of the conversion factor, because what that will do for me is that puts days opposite. I have days up top and I have days down bottom, so they're going to cancel out. And I'm going to be left with hours. And I do the calculation and I find that I have 72 hours. Let's say I'm going the other way. I want to know maybe how many days are in, we'll say, sorry, go away. If I have 48 hours and I want to convert that over to days, now I'm going to use this form of my conversion factor, because what that's going to do for me is now I have hours up top and hours down bottom. They'll cancel out. And so I'm left with days. And so now I would do 48 divided by 24, and I would come up with a final answer of 2 days. And so when you're doing converting like this, when you're doing these conversion factors, when you get to the point of actually calculating using dimensional analysis, you take everything that's up top, multiply that through, then everything down bottom, multiply that through, and then you divide them. And so in this example here, I would have had 48 times 1, all divided by, and you can sort of view this as a 1 if that's helpful to you. 1 times 24, and we get our 2. So multiply through everything up top, multiply through everything down bottom, and then divide. Dimensional analysis is an incredible tool because it will help you set up calculations even if you don't remember how you're supposed to actually run the calculation. So let's look at actually at a couple different homework problems. And so here's question 34 in your homework. And so now we're working with time again. And we need to convert, in this case, 2.3 hours over to seconds. And so one of the things that I like about Chem 101 is that it does have these dimensional analysis setups so that we can work with dimensional analysis and look at our conversion factors. And so we start here with our starting amount. And so our starting amount we're given is 2.3 hours. And so we're going to drag those in here. It might be helpful for you to put the answer box in here now, just for the units. We're not going to put a number in there yet, because we don't know. We haven't calculated it yet. But it might help you keep track of what you're trying to get to. Oops, sorry. There we go. And so now we have seconds up there in what we're trying to find. And so we're trying to convert 2.3 hours over to seconds. And so we know that our conversions that we're going to need to get there is, first we're going to need to go from hours over to minutes, and then minutes to seconds. And so maybe you want to, depending on how you want to do this, maybe you want to put the actual units in there first. So again, we need hours to cancel out. So that needs to go down bottom here because it's up top over in our starting number. And so this shows us now that hours are going to cancel out. So that's good. And we're going to want to convert to minutes. And we know that there are 60 minutes per 1 hour. And so there's our first conversion. We need to add in another conversion factor now in order to get from minutes over to seconds. You can see that we want minutes to cancel out. So we're going to put that down bottom. We want to end up with seconds. And we know that there are 60 seconds per 1 minute. And so now it's keeping track of it for us down here as well. And so we can see from our units that everything is canceled out that we need to cancel out. We're left with seconds, which is what we want. So it looks like we might be done. And so let's put this into our calculator. We have 2.3 times 60 times 60 gives us an answer of 8220, which luckily is one of our options. So we get 8220 seconds. See if we were right. Remembering that there is a 10% penalty for each incorrect attempt. We got it right. Good. Let's look at another example. Let's go ahead and do our millimeters to inches. We'll do this one. And so here's where you might have to look up some other conversions. You might not know what the conversion is straight from millimeters to inches, but you might know that there are 2.54 centimeters per inch. That's a fairly common conversion. And some of these, feel free to look them up as you're working, because I wouldn't expect you to know centimeters or millimeters to inches. That's not a common conversion that you might know off the top of your head. So feel free to look some of these up as you're working. We're going to put in our starting amounts here. So we're starting with 34 millimeters. Again, I find that it might be helpful for you to put in at least the units of what we're looking for, so you're kind of keeping track. So we need to go over to inches. Like I said, we do know, we can even add it in here if it's helpful at this point, because we do know a conversion to go between centimeters and inches. We know that there are 2.54 centimeters per every 1 inch. But now we need to go from millimeters over to centimeters. So we're going to need millimeters to cancel out. Centimeters, which now cancels out here, so that's good. So now we have to think about our conversion between millimeters and centimeters. A couple different ways you could go about this. You could either, just looking back at our metric conversions, recognize that there are 10 millimeters per every 1 centimeter. It's one way to do it. You may find it easier with metric conversions as you're starting out. It might be easier for you to convert back to the base unit first, and that's fine. In that case, you would have converted from millimeters to meters, and then from meters to centimeters. That's okay too. It'll be the same thing either way. But now we see what we have here. And so we've got our 3 point. Let's just sort of look at what this would look like into the calculator. And so again, we're going to take everything up top. And so we've got our 34.0 times 1 times 1. That's everything in the top of our conversions. And then we're going to have 10 times 2.54. And we're going to calculate that out. And so we put that into our calculator. We can make judicious use of parentheses. So I'm going to go parentheses 34. Sometimes, especially as you're just starting out with these, you might find it handy to put the ones in there. So 34 times 1 times 1. divided by, close parenthesis, divided by, I'll open up parentheses again, 10 times 2.54, close parenthesis, and I get an answer of 1.338. I round for my significant figures. My initial measurement started off with 3. So I get 1.34 inches, which is one of our choices. Let's put that in. We'll see if we're right. Look at that. Let's get one more fairly complicated example. Now, normally I won't go through a lot of your homework problems like this, but I really wanted to show these dimensional analysis examples. All right, so here we're told that a fuel tank holds 23 or 22.3 gallons of gas. We're given the density of that gas, and now we want to go to the mass in kilograms. Density is just another conversion factor. And so in this case, we've got a density of 0.8206 grams per 1 milliliter. Depending on how we want to use that conversion, though, we might use it either way. And so density is just another conversion factor converting between grams and milliliters. And so let's take a look at this problem. So again, we've got our starting amounts. We have our 22.3 gallons. And we eventually want to get to a mass in kilograms. And so we know that we're going to use our density as our conversion to go in between our volume of gallons and our mass in kilograms. But we've got to figure out how we're going to get there. And so again, this might be where you want to look up some different conversions. And so for instance, we know that we're working with our density here, which is going to be in our volume units are going to be milliliters, and our base unit for volume is liters. And so maybe we want to know how to go from gallons over to liters. This is again where it's fine to go ahead and look those up. And so I'm going to look up gallon to liter. And I'm going to see that there's 3.785 liters per 1 gallon. So here it is. 3.785 liters per my 1 gallon. So far, so good. But now I'm still going to need to go to milliliters in order to use my density here. And so I'm going to add in another factor and convert over to milliliters. I know that there are 1,000 milliliters per 1 liter. And this is where I was saying earlier, this is how you can use dimensional analysis to do your metric conversions as well. And so 1,000 milliliters per 1 liter. So great. Now I'm at milliliters. Still need to get to kilograms. I see that I can use my density to get to grams from milliliters. So let's put that one in. I've got 0.8206 grams per every 1 milliliter. That's my density. Okay, we're almost there. Now we'd be at grams if we ended, but we want an answer in kilograms. So we have one last metric conversion to do. We want to go over to kilograms from grams. And so we know that there are 1,000 grams per 1 kilogram. And so we can see unit-wise that this works out. Our gallons cancel, our liters cancel, our milliliters cancel, our grams cancel. We're left with kilograms. Those are the units that we're looking for. And so we need to see if this is actually going to work as far as our conversions. So I'll leave this up, but then I'll switch over and show you how it would look. Maybe typing it in. We're going to take our 22.3 times 3.785 times 1,000 times 0.8206 times 1, all divided by 1 times 1 times 1 times 1,000. So it would look something like this. And that's what you would then put into your calculator. And so let's see what our calculator gives us when we actually put this in. We're going to get 22.3 times 3.785, 0.785 times 1,000 times 0.8206, all divided by 1,000, gives us, rounding for significant figures, our lowest number of significant figures is 3 from our measurement here. And so we round this to 69.3 kilograms. And we got it right. And so that's how you would use dimensional analysis to solve this problem. Okay, that's actually all for today. Go ahead and look through this problem solving technique on your own. Look through the lecture notes and take a look at just at how we can take various problem solving approaches. But then that is all for today. I know that is a lot. That is nearly an hour and a half of lecture. Hopefully you didn't watch it all in one shot and you took a break partway through, because it's a lot to watch at one time. Like I said earlier, I will try to keep the lectures as much as I can to about an hour 15, which would be approximately the length of time if we were live. But that is one of the advantages to the online lectures as opposed to live, is that sometimes if I need to, I can go a little bit over. And so I might on occasion in times like this, because I'm able to give a lot more examples, because I've got a little bit of that time flexibility. And so that is it for today. Make sure to email me if you have any questions, work on the homework, and have a great day. And you get to watch me for a little bit longer as I get to stopping the recording. There we go. See you later.